Perfect. Yeah, so this is the first episode in our research talk series on robotics in medicine, or robotic AI in medicine. So we're excited to have Haojun be the first guest. The way this is going to go is it's Haojun is going to give a talk about his recent work on ultrasonography for carotid artery screening. And then there'll be a short Q&A after where anybody can ask any questions. So yeah, if you have questions, reserve them till the end, and then we'll have a back and forth with Haojun. And yeah, Haojun, take it away.
Okay, I will share my screen. Can you see my screen?
Yep.
Okay. Hello everyone. I'm Haojun Jiang from Tsinghua University. First, I want to thank Professor Pranav and Dr. Xiaoman Zhang and Roman Hardy for the invitation. It's a pleasure to be here, especially for the first one to share the work. Yeah. Today I will begin with a brief introduction to my PhD research entitled Towards AI-driven cardiovascular ultrasonographer via large-scale implicit structural learning. But I will focus primarily on the Nature communication paper related on the carotid artery robot. So the beginning part is mainly about the background and overview of my PhD research work. Well, my research is conducted under the guidance of Associate Professor Gao Huang from the Learning and Perception Lab. And you can find more information about our lab at the website. And now a bit about my background. My research focused on three key areas: robotic, ultrasound, multimodal learning, and efficient deep learning. And to date, I've contributed as first and or co-first author to 8 publications in top journals and conference, such as Nature Communication, Pattern Recognition, CPR, and MICAI. Well, uh, then let's dive into the robotic ultrasound. Well, first, why do we need AI for cardiovascular ultrasound? Let's start with the limitation of the manual examination. Well, ultrasound examination is highly reliant on manual operation, particularly in cardiac ultrasound, which demands extensive expertise. Well, this results in a shortage of qualified sonographer. Furthermore, variability in different operators leads to low standardization and poor repeatability. And prolonged operation also causes fatigue, ultimately compromising the examination quality. Well, to address these limitations, we propose to build a AI sonographer that analyzes the ultrasound image to determine the next optimal scanning decision. And this system has the capability to guide less experienced sonographer to perform high quality scanning and also driven the robot to do a fully autonomous scanning. Well, how to build a AI sonographer? I think there are three main challenges we have to solve. The first one is we need to enabling the model to understand the 3D structure of the organ. Well, in ultrasound scanning, where 2D slides are used to view the organs, and so the comprehending the 3D structure is come down to modeling the relationship between different 2D slides. And second, there are huge inter-subject variability in anatomy between different individuals. So the scanning strategy or the scanning model we build have to adapt to this kind of variability. And the third challenge is ultrasound is conducted in is conducted with limited computing power, but it also need high frequency of interaction with human body. So in the ultrasound scanning, we have to build some lightweight neural networks to support real-time perception and decision making. Well, to overcome these challenges, our core strategy is imitation learning. Well, our key insight is that uh, if a sonographer can perform a scan successfully, they need to understanding of the 3D structure, and they have to have acquire the ability to adapt to the individual variations. So uh, based on this insight, we collect two large-scale data set and learning the knowledge required for the ultrasound scanning through the data. And finally, we build two models which can input ultrasound image and given a target plane or defined a scanning task, the model can output the probe adjustment action. Then for cardiac, since it is more complicated, the structure is for heart is more complex. So the adjustment action need to be decide in predict in a continuous space. While for carotid, it's a much simpler organ, so we output discrete actions. Well, to support the imitation learning strategy, we collect two large-scale expert demonstration data on real person. The cardiac data set comprises 178 subjects, and the carotid artery data set comprises 81 subjects. And the data for cardiac is acquired by uh, direct control probe attached to a Franca Panda robotic arm, which means the sonographer will hold the probe and conducting the scanning, and our system will record uh, the trajectory or the pulse of the probe and its corresponding ultrasound image. Well, for carotid data set, since we discrete the action to we use tele control. It's like well, the probe have 6 degrees of freedom, and each freedom have two directions. So we have 12 discrete action, and we map the each action to the keyboard. So the sonographer can press the keyboard, and the robotic arm will accurate the corresponding action. And we record the action and also the ultrasound image. Well, this slide's overview summarizes my doctoral research, which address the aforementioned three challenges, like modeling the structure and adapt to the individual variation and the real-time inference on edge devices. Well, we focus on cardiovascular, like carotid artery and also the heart. And based on this advancement, we build a robotic prototype and conduct preliminary clinical-oriented validations. Well, okay. Uh, the above give a brief introduction to my PhD thesis or PhD works, and now I will introduce our work published in Nature Communication. And I'm deeply grateful to my advisor and collaborators and many others who supported this work. First, our work focuses on carotid artery. It's a major blood vessel connecting the heart and the brain. As people age, plaque will build up in this artery, causing it to narrow and leading to high blood pressure. For this, for this reason, patients need regular ultrasound scans. And in this work, we build a fully autonomous robotic system powered by an AI model. It is capable of performing autonomous scan based on the scanning decision output by our model. And after obtaining all the key anatomical structure or the high quality ultrasound image, we can perform biometric measurement and plaque screening. Based on all the results, the system will output a structured examination report, which reflects the subject's blood health. Well, before diving into the detail, let's look at the demos of our carotid robot. This is the robotic ultrasound examination of a 65 years old patient with plaques. Well, the area highlighted by the red box is the blood vessel we need to scan. The robot first scan the transverse views of this artery, and the ultrasound probe is attached to the end of a Frankopanda robotic arm, and our model provides real-time movement commands to guide it along the entire length of the artery. Well, here it is scanning the transverse view, and later it will switch to the longitude view now. Yeah. Scanning the longitude view is significantly more challenging than the transverse view, as the blood vessel is only 5 to 8 millimeters, and this requiring precise adjustment to probe positions. And following the scan, we perform some biometric measurements and plaque screening and the blood flow assessment. The final result includes high quality images and corresponding measurement data. Well, we are not the first to work on carotid artery scanning. One category of existing work is rule-based methods. A typical work I present here, it treats the vessels as simple tubes and manually defined adjustment strategy based on the image features from different probe angles. And but this approach failed to generalize because it didn't count for the real-world variation in vessels. Another category of work used reinforcement learning. However, it faced the same issues, being trained in a simulation with simplified vessels models, also limit its real-world performance. Prior to our work, a study on robotic cerebral ultrasound was also published in Nature Communication. This paper did excellent work on the downstream diagnostic task, and we have learned a lot from it. However, in terms of the scanning target itself, the cerebral is a larger organ with less anatomical variations, making it less challenging to scan than the carotid artery. Meanwhile, it uses a hybrid control strategy that combines rules with learnings, which made the entire system quite complex. Also, I think such a complex strategy is hard to adapt to other organs. Well, moreover, we have summarized the limitations of the prior work into four key aspects in our paper. First, the existing work are mostly rule-based, and rule-based. The lack of flexibility and struggle to adapt to the complex structural variation of the carotid artery in the real world. And second, the previous work laid the action decision data. You can see a lot of work collect thousands of data in perception. All the work collect thousands of data in perception, but none of them have data about the scanning. So that makes it impossible to train a learning-based scanning model, which also limits its generalization ability. Third, the scanning protocol is incomplete. It focuses only like on scanning without linking to the downstream biometric measurement and plaque screening. Finally, the validation in previous work were done in a relative small scale. Uh, the maximum people they validate is three unseen people, and in our work we validate on 41 people. Also, we not only evaluate the model from the success rate, which means the robotic system can acquire like high quality ultrasound image. We also evaluate from the perspective like repeatability, consistent with doctors and comfort, and also quantitative errors. Well, uh, now let's first start with the methodology. As I mentioned above, motivate our work is motivated by recent advances like in large language models or other compute large scale computer vision models like SAM. We adopt a fully data-driven strategy uh, that is imitation learning from the expert scanning. Well, also, I already mentioned that the expert data uh, is implicit embedded with the knowledge like structure and the ability to interpret the ultrasound image. Also, the operational skills to like adjust proper angles to obtain high quality images. Well, uh, I think this pattern has the advantages of scaling up. And in the future, if the ultrasound robot can be deployed in real clinical in hospital, like the data set will continue growth. Also, the scanning data is actually exists in hospital, but there are no proper sensors to record the action conducted by the sonographer. So if someone can build a cheap and effective sensor uh, for recording the expert scanning, I think this kind of strategy has much more power. And with the data scaling, this will continuously improve the model's performance, steadily approaching the levels of expert sonographer. Well, for carotid artery, we discretize the action space, which means the probe has 6 degrees of freedom. And in each degree, then we have two directions. Like in this axis, we have the probe can move right or move left. So our model we during the data collection we collect discrete actions like finally and we have as the diagram shown in the middle uh, our sample contains image and its corresponding adjustment actions. And the final data set includes 81 subjects, totaling 0.25 million samples. And based on the data set, we build an end-to-end vision navigation model, which takes current ultrasound image as input and directly output the discrete probe movement to check the artery. And this combines with the stage switch model that identify the current anatomical target, and which means if the model found the target structure is already exist in the ultrasound image, then the model will know this scanning subtask is finished and it will switch to the next state. And I think this paradigm has three advantages. First, it integrates perception with the decision making, and it allows the visual feature learned by the model to be directly optimized for the scanning task and makes the process more efficient. Also, we use discrete actions, and this approach, first, the discrete action can meet the scanning requirements for the carotid artery. And by discreting the decision space, we simplifying the optimization complexity and made the model easy to converge. Finally, we use a unified learning strategy to handle adjustment across all degree of freedom and different scanning subtasks. Well, after the scanning is complete, we have designed models for measurement and plaque screening to achieve a fully autonomous ultrasound examination workflow. This diagram shows the complete process for acquiring key anatomical structures. Here is the transverse view of the artery, and here is the longitudinal of artery. And in these images, we can clearly identify the plaque in the patient. And based on this high quality image, we conduct the measurement, segmentation, and also blood flow assessment using color and pulse Doppler. Based on all the results, the system generates a structured report that summarizes the subject's health status. Well, in order to validate our system performance, we conduct a real-world evaluation with three senior sonographers on 41 unseen subjects. First of all, we let the robotic system perform the fully autonomous scanning and measurement on a group of subjects, while the sonographer also completely manually. The sonographer will manually perform the same procedure on the same subject. Then we can get two group of data that is obtained by robotic system and the sonographer respectively, and we apply blend ultimate analysis, which shows that the measurement from the two methods were in agreement. In other words, our robotic system is capable of acquiring high quality ultrasound images and performing accurate measurement. Well, second, to access the repeatability, the robotic system and the sonographer each performed three scans and measurements on the same subject, and the consistency across these three measurements was then evaluated. As we can see from this image, or the four matrix to evaluate the consistent demonstrates the superior repeatability for our robotic system, which is much more the results in three scans or in three measurements in much more consistency for our robotic system than the sonographer. And the third, we record the contact force to the neck, and the force it was maintained within a safe and comfortable range. And finally, in terms of efficiency, uh, please first look at the left image, which shows the measurement time. And our robotic system using AI algorithm for measurement is significantly faster than manual measurement by a sonographer. However, it's like it's 40 times faster than sonography in average. And however, in terms of scanning, the sonographer is much more efficient than the robot. The flexibility of the human hand is still far superior than the robotic arm. And ultimately, our system achieves total scan and measurement time comparable to that of a sonographer. We also test the system robustness across multiple key dimensions, including patient age and BMI and the different ultrasound imaging machines from different brand. One is from GE and another is a Chinese brand High. And also we test different imaging parameters. And the result here shows the consistent performance across all conditions, demonstration the robustness of our robotic system. And I think this is also a advantage of data-driven approach. If you have more data, the model can see more possibilities and it will perform better in real world. And also compared to previous works, our method achieves better performance on a large population and enables more comprehensive scans, covering more key anatomical structures. We also verifies on offline data sets that increase the amount of data from 10% to 100%, and it shows the performance will continue to improve as the data size grows. And in the future, as even more data become available, the overall performance of the robot system will continues to improve. Well, finally, our work makes key contributions in these four areas. First, our methodology. We introduce a unified imitation learning strategy that controls all degrees of freedoms and works across all scanning stages. Second, we created the first large-scale dataset of carotid expert scanning demonstration. And the third, in application, our system achieved full autonomy, covering key anatomical structures and completing the entire workflow from scanning, measurement, and to screening. Finally, we conduct clinical-oriented validations on a large population, on a larger population, demonstrating strong real-world performance. Well, this will the introduction about the Nature Communication paper is end now, and in this slides. I will conclude my PhD research. My research focus on advancing the intelligence of the ultrasound scanning, focus on these three challenges or three part research and apply the algorithm to AI-guided scanning for novice or less experienced sonographer, and also driven robotics ultrasound. But in the future, I think the most important thing is still the data. Yeah, uh, in the in the uh, the data we collected is not real clinical data. It's not collected in like a big hospital. So in the future, if we want to apply the ultrasound robotic to a hospital, I think the clinical data is the most important. And second, um, since my work is all following the imitation learning strategy, and at this moment, um, we also conduct a lot of experiments on real patient, and we found it's kind of the imitation learning strategy has performance limitations on harder case. In the future, I want to or in other words, the imitation learning strategy we adopt now makes the model like make decisions in an open loop manner, and in whatever situation it will output an action, and it can't after output the scanning action, it can't evaluate its decision. So, in the future, I think we need to uh, develop a high-level reward model or ultrasound imaging quality assessing model. It can provide real-time feedback to the decision model, tell the model uh, the decision you made just make the image quality better or worse. Yeah, and in application, we are working on carotid artery and heart now. In the future, well, in hospital, I think scanning like liver or other organs is also very important. So. The second point is what we are doing is standardization the scanning protocol. But in real clinical environments, not everyone apply the same protocol. Sonographer will adjust the scanning strategy or scanning protocol based on this personal situation. So I think the second interesting point is from standardization to personalization. Also, at this time, we can capable doing scanning and diagnosis. Maybe in the future, we can also integrate like ultrasound guide intervention with the scanning robot. Yeah. Well, to conclude, the long-term goal uh, for my research is to build an intelligent ultrasound robot for multi-organ scanning, diagnosis, and treatment. Well, this is all my presentations, and thank you for listening. And if you have any questions, please just ask, and I will tell all the knowledge I have in the last few years.
Thank you so much, Haojun. Yeah, this is really, really great work and really exciting stuff. So I think we'll open it up for public questions first, and then we can maybe do a private Q&A in the last 10 minutes if anybody has any questions they don't want to appear on YouTube, or if you want to keep a subset of questions for just this discussion. Um, so yeah, maybe if you have a question, use a little hand up emoji and I can just call on people.
I'll start with one. So, Ajahn, you described sort of two approaches earlier. One was the sort of direct approach, and one was um, the remote approach, I think is what you called it. Could you just talk about your experience with both of them and sort of um, what worked and what didn't?
You mean the data collection approach?
That's right.
Well, I think this two kind of approach is not the best strategy to collecting data, since from my experience, telecontrol is quite uh, uh, it need a lot of time. Yeah, human sonographer can directly control the probe. It will make the collecting process very inefficient. Yeah, and the direct control uh, mode also has some problems. Like we have to design some control strategy for the robotic arm. We should make the robotic arm can follow the humans' actions. Although did a lot of effort in developing like a control algorithm, but it's still very hard for sonographer to use. And I think in real hospital, uh, it's impossible to deploy a robotic arm for data collecting. Well, yeah, that's my opinion. And in the future, I think the best way is use like optical tracker. I know a good product is built by named NDI. It can check like we can put some marker on the ultrasound probe. It's very small markers, and it will not interface ultrasound scanning procedure. So you can just put a optical camera uh,
Yep.
along the sonographer, and it will not make their daily scanning more difficult. Yeah,
Sure.
I think the optical tracker is a much more better way to collect data.
Optical tracker without attachment to the robot or with attachment to the robot?
With without attached to a robot.
Okay,
The optical tracking camera is a kind of individual camera put alongside the
sure.
alongside the bed. Yeah.
Yeah, that makes sense. I guess if you were doing the optical tracking approach, the idea would be that you would still get the positioning at different time points, but you
Yeah,
would
yeah,
not
yeah.
necessarily get the force application.
But force application? What do you mean force?
You would not be able to recover how hard someone is pressing down on.
Oh, yeah, yeah, yeah,
Okay,
of course. Yeah. Maybe you have another like a force sensor
yep, other.
attached to the probe.
That
Yeah.
makes sense. My second question, before I pass it on to others, is in your neural network setup, could you just describe once again what the input space and the action space are?
Well, for the carotid artery, the input is only the ultrasound image. But I think this is not enough. For carotid artery, only based on make decision only based on the ultrasound image is enough. But for other organs like livers, maybe you should give like force to or give the force as input. Also, maybe the RGB camera, uh, like a multimodal data for the uh, decision model. Yeah. In this work, we output like discrete actions. Yeah. They are the probe have 6 degrees of freedom, and each freedom have two directions. So in total, there are 12 discrete actions. Uh, well,
Well, I guess, yeah, is the idea that you are supposed to have started with sort of like enough force into the, the neck that you always start with an ultrasound image as input? Because if you
yeah, yeah,
imagine
yeah.
sort of like if you're not on the skin, there's nothing on the ultrasound, how do you decide what action to take?
Yeah, that's a good question. So if the probe not attached to the neck, there were no ultrasound image, so the model can do any decisions. If in this situation we need a RGB camera, yeah, RGBD camera with depth information, so we can estimate the neck's position. So and we send this information to the robotic arm, and it can approach the probe to make the contacts with neck again. Yeah,
I see. Thank you.
yeah.
Um,
But in this paper, we actually we didn't explore how to approach the probe to the neck, since I think this kind of work is really important in application, but it don't have uh, it don't have any credit in research paper. So we just focus on the scanning part. Yeah,
Makes
scanning
sense.
decision part. Yeah.
Makes sense. Thanks.
I think Xiaoman had a question. I can read it out. So, following Pranav's first question, I think these two methods obtain data in different formats. Will the sample size or training complexity change as a result?
Can you repeat it again in a slow
Yeah. Oh, sorry,
speed?
sorry. Yeah. So Xiaoman asks, following Pranav's first question, I think these two methods obtain data in different formats. Will the sample size or training complexity change as a result? So
Uh,
collecting data with an external sensor, I think, versus kind of the discrete keystrokes.
mhm. Well, I think it can all collect in the by the NDI tracker in the future, optical tracker. Uh, mm, sorry, can you repeat it again? I didn't understand it.
Yeah, I
I
think
think
if
I can explain it more. So my questions like the direct control the data you are collect is the like the trajectory of the probe, but for the telecontrol the data you are collect is the like discrete sample points. So I think
Yeah.
the like the model training for if it's discrete, then you like when you scan one time you will have a lot of like action points there, but if it's direct control for each scan, you only have one like trajectory, so the like the sample size will be different. So for the direct control, do you need to collect more data to train the models?
Uh, First, these two kind of data collection uh, protocol mm, is mainly uh, depended on the scanning difficulty of the organ. Uh, for the cardiac ultrasound scanning, you can't apply telecontrol. Yeah, and
Mhm.
the reason we apply direct control for cardiac ultrasound, it is the scanning adjustment action during the cardiac ultrasound is like not only in 1 degree of freedom, but multiple degree of freedom. It's a compound action. Yeah. Well, uh, I think these two kind of data collection strategy will not impact how much data you need to collect. The real the key question is the difficulty of the scanning of the difficulty of scanning the organ. Yeah.
Makes sense. And I have another question is like when after you training the model and before you do the like real world patient experiments, how did you like validate the model's performance? Because I think you don't have any phantoms and you're training on like the data you collection. So like how can you know it will not hurt the patient or like have like the wrong action during the real clinical experiments?
Yeah, that's a good question. Uh, for the model performance, in the paper we show some offline results, like about the accuracy of the action decision, and it's like about uh, I didn't remember I don't remember the exact number. It's like 80, 85 to 90% accuracy. And for the second point you mentioned is the safety. Uh, mm, you mean if the robot conduct output a wrong action, it may hurt the people, right? Yeah. In terms of this point, we actually develop something control algorithm in robotic arm. We will force the robotic arm. We will force the contact for. We will constrain the contact force between the probe to the human surface to be lower than like 4 Newton. Then, although it output a wrong direction, if the contact force is larger than 4 Newton, the robotic arm will not uh, move forward. It will stop there. Yeah. The safety is achieved by the control algorithm. Yeah.
Thank you. Yeah.
Uh, the methodology about the control algorithm is in the method part of my paper. Yeah.
Congratulations on all of this.
Yeah, thank you. Thank you very much. It's also my pleasure to share my work. The first time in English.
Is that right? Okay.
Yeah, I've been sharing my work in Chinese for like many times, but this is the first time for English. Yeah,
Yeah,
in
that's right.
English.
I was asking someone in the lab to share their practice faculty talk, and they said it's all going to be in Chinese. And I said, "Wow, that's I can't be helpful with that." So,
Yeah,
anyways,
yeah.
awesome. Congrats. Great. Roman, any final words?
No, I guess I'll just reiterate what you said. Thank you so much, Haojun. And thank you for presenting for the first time in English. I think you did a great job. Apologies for speaking too fast at times. And yeah, we look forward to seeing what you'll publish next in in the
Yeah.
robotic space.
Yeah, maybe in the 2 months, maybe in the uh, later of this year, I will make the cardiac ultrasound robots public available. Yeah, I'm working on it, and we've been working on the cardiac ultrasound for like 3 years. Yeah,
Very nice.
That's
Yeah, very exciting stuff.
Mm.
awesome.
Awesome. Yeah, in that case, I'll end the recording and Well, good night to you, Haojun, and good rest of the day to everyone else.
Yeah.
All
Thank you
right,
very
thank you so
much.
much.
See you.
Bye.